Okay. So in today's class, we're going to return to doing the path integral. We're going to return to doing the path integral over the world volume of the string. Okay? We're going to return to doing the path integral over the world volume of the string, but this time more systematically. So to quantize the motion of the string, but this time more systematically than our first class. As you remember, the action that we were interested in was 1 over 4 pi alpha prime square root g del alpha x del beta x mu g alpha beta. You remember from our first couple of lectures that we decided that this was the action of interest to us. Okay? And what we're going to do is to try to evaluate the Euclidean path integral dg alpha beta dx e to the power minus s, where s is equal to this. Everything here is equal. At some point, I'll take you through a careful understanding of the the analytic continuation that takes the Lorentzian path integral and the Euclidean path integral. So let's leave that till we've understood the Euclidean path. Okay? Any Lorentzian quantity you want to compute, you compute once you know the instance. With appropriate concessions. Okay. So, the key point, of course, was that this action was to be thought of as an action of the gauge integrals. What were the gauge symmetries? There was diffeomorphisms on the world sheet of the string, and there was Weyl transformations. Okay? So if you just try to do this action, this path integral, for instance, in perturbation theory, you get divergences. Because there are flat directions associated with gauge transformations. But we know now that we're all grown-ups, we know how to deal with such problems. Okay? We know that there is a very clever trick to that allows us to deal with such problems. That trick is called Faddeev-Popov. Alright? So, let me review the Faddeev-Popov method in the context of interest. Let us suppose that I choose some sort of fiducial metric. I call that G hat. Let zeta denote the space of gauge transformations. So zeta denotes both coordinate transformations as well as point transformations. And let me assume for perhaps the first term of this lecture. Obviously it's not precise. Let me assume, because you don't want to do everything very precisely the first term. Don't have to understand. Let me assume that we find this to some small degree untrue, more or less true, that it is possible to completely take any metric and by a Weyl and a diffeomorphism transformation, okay, transform it to the form we have. So for instance, if we're interested in metrics on the sphere, the two-dimensional sphere, let me assume that you choose a canonical metric on the two-dimensional sphere, for instance, the round metric. Okay, and let me assume that that it is possible always possible to take an arbitrary metric of the sphere and by a Weyl diffeomorphism transformation transform it to the round metric of the sphere, and moreover that choice is unique, that completely fixes gauge. Actually, we will find there are no manifold on both these statements. Whether it's possible to take an arbitrary metric and by Weyl diffeomorphisms bring it to a fiducial metric depends on the manifold we're working on. We will see this. In fact, on the sphere, if the manifold was a two-sphere, it turns out to be possible. But that's the second part, that not only do we want it to be it's possible to take an arbitrary metric to a standard form, we want that condition to completely fix gauge invariance. On this pair, we will find that there is a 6 parameter or 3 complex parameter worth of gauge invariances that are left unfixed by this requirement. On the torus, we'll find that it's not possible to take an arbitrary metric to a standard form, but it's possible to take it to one member of a one complex parameter set of standard forms. Okay? And that choice leaves a one complex parameter set of gauge invariances unfixed. On higher Arrhenius manifolds, we will find that it's not possible to take it to a standard form, that the number of parameters that you have to put grows with the genus, 2g minus 2, complex parameters, but that once you put it in this form, it completely exhausts all gauge invariants. So, on some manifolds, one condition is possible to meet, some manifolds, the other condition is possible to meet, no manifold that both of them possible to meet. So, our assumption is not completely true, not completely right, but we deal with this. I just don't want to do everything at the same time. Okay? So, though it's not completely possible, let's deal with that, we'll come back to looking at it. Okay. Okay? So that's not completely true. We assume that every metric can be put, that there is a gauge transformation that takes this g hat to any metric, and that the gauge transformation that takes g hat to any particular metric is unique. Okay? So that g hat is effectively a good gauge fixing condition. That the metric is g hat. It's a good gauge fixing condition. Because here. Suppose this were true. Okay? Suppose this were true. Then what we can do is the following. Inside this path integral. Okay? So then let's look at this auxiliary device. Suppose I get delta of g hat zeta minus g. G is the truth. Is some metric. We'll soon identify it with this metric that we're path integrating. And I integrate this over all gauge transformations. Roughly speaking, what do I get? Well, this delta function clicks exactly once. It clicks once and exactly once because of our assumptions. Our assumptions were that there's exactly one value of zeta that takes g hat to any g. And that there is one and that there's exactly one. The delta function clicks once. Now, roughly speaking, this answer is 1. This thing's 1. But it's not quite 1, okay? Because there's a major factor. For instance, delta of x square minus x naught square integral 0 to infinity dx clicks exactly once. Clicks at x equals x naught. But the answer is not 1. It's 1 over 2x naught. As you know, right? It's 1 over x prime. The delta is a major factor. So, this quantity is roughly 1. It's not quite 1. Whatever it is, we will call 1 over delta phi. It's the major factor that makes this not quite 1. That's what the Faddeev-Popov determinant is for this gauge fixing procedure. Now we want to understand what this Faddeev-Popov determinant depends on. Okay? In particular, I want to understand whether it depends on the choice of G. Okay? I want to understand whether it depends on the choice of G. Now, the answer is that it does not depend on the choice of G, as we can see from the following formal manipulation. See, consider delta of g hat zeta minus g. Now, since all g's, according to our assumption, can be taken from one to the other by one of these gauge transformations. Okay. Suppose I look at g, the dependence on g is entirely captured by taking some gauge transformation of g. So this is equal to 1 over delta f3 of g of zeta naught.
the fact that we're taking all the gauge freedom as a gauge freedom of G doesn't mean that there's no gauge freedom left on the sigma term.
Sigma is what?
The worldsheet coordinates. Like,
see, the gauge freedom acts on all fields in the theory. Quantities are just parameters.
right.
So it acts on fields. It acts on x's and it acts on g's. Right? So how does the diffeomorphism act on x's? It acts by how a scalar acts. How does it act on g's? It acts how a diffeomorphism acts on g's. Linear direct. Okay? So it's not that the diffeomorphisms act only on g's and don't act on x's. They do act on x's. But we're going to do our gauge fixing procedure by using gauge transformations to set G to a particular form. We could equivalently have tried to set X to something. But this is a nicer thing to do because we will not violate space-time. Okay? So the kind of thing we did in the first class was a canonical form of what you're talking about. Like gauge. Now we're trying to do something different. Okay? So we're choosing G by choice, not because that's the only thing that diffeomorphism acts. I'm choosing that formation. Okay. So this, by definition, is one over the Faddeev-Popov determinant of G of zeta. But now, if we are able to do this formal integration over delta functions with a measure that's gauge invariant, and if we are able to define this delta function, whatever it is, in a manner that is gauge invariant, then formal manipulations now show that this does not depend on theta. What are the formal manipulations? The formal manipulations are that because this delta function is because this delta function is gauge invariant, we get the same answer. We just gauge transform everything. So we gauge transform by zeta not inverse. Okay. So this becomes G and this becomes zeta not inverse. Zeta times zeta. Multiplied to transformation. Then we'll also assume that our integration measure, which is d zeta, is gauge invariant. And therefore, if we define this as zeta prime, d zeta is the same as d zeta prime. So this is delta of G hat, zeta prime minus G. But this now is the definition of the 1 over the Faddeev-Popov determinant of G. Okay. Now some of you are thinking, wow, this is formal stuff. There's a zillion ways in which all this can fail. Right? And it's true, okay. Yeah, it's true that you have to be very careful. We've not worried about regulators, we've not worried about exactly how this measure is defined, delta function. In this game though, it's usually not very productive to try to make these kind of steps too rigorous. Because it is true that when you're dealing with these infinite dimensional path integrals, many things can fail. Okay. The attitude we're going to take is we will do reasonable sounding manipulations and see if we land on our feet. By which we mean, do I get formulas which make sense, which pass all consistency? Okay? That's the attitude we're going to take. The thing I'm going to tell you about is sometimes called the heuristic derivation of this string S matrix, as opposed to the rigorous derivation which doesn't exist. Yeah. Okay. Great. So what we concluded is that this Faddeev-Popov determinant is independent of G. It can depend on G hat. Okay? It's independent of G. For those of you who are seeing the Faddeev-Popov procedure for the first time, a useful arena in which to play with this, I think in the last quantum field theory course we discussed this, is in the integral over a two-dimensional plane. The integral over a two-dimensional, basically what's a gauge theory? You take a field configuration space, slice it up into gauge orbits. So that's like the gauge orbits are rotation orbits in the two-dimensional plane. Okay? So an integral is an integral over r times an integral over theta. Now, the key point is we will only be interested in integrating gauge invariants. So we can do the integral over theta once and for all. So we can choose a Fourier-Popov slice. Make all functions functions of the x coordinate in the positive x direction. So integral over the two-dimensional plane translates into integral over x or integral over r, but with some measure. We know the right measure is r dr, 2 pi r and r. And this Fourier-Popov method, when applied to this thing, can be used to derive the 2 pi r. Okay? If you're not familiar with this, you can come to me or you can try it as an exercise. Okay? So if you encounter the Fourier-Popov method for the first time, you need to play around a bit because it sounds weird. You have to convince yourself that you're not fooling yourself. It's good to try simple examples with finite integrals where it's really rigorous. Okay? But I'm going to just assume that most of you have encountered Fourier-Popov before. Okay. So now we have this nice identity, that is delta fp times this integral is 1. So 1 has the lovely property that multiplying anything, it gives back itself. So we've got our path integral here, dx dg e to the power minus s of x and g, and then just in the integrand of the path integral, I'll multiply the integrand of that path integral by 1. But 1 is that. So I can multiply the integrand of a path integral by integral delta g minus g at zeta d zeta times delta ft.
This delta ft, you can see from the other side, is only a function
of g hat, of the fiducian metric. Yes, exactly. This is delta fp of g hat. Now, I interchange orders of integration. I take this d zeta out here, e to the power minus s, x, g, delta fp of g hat, delta of g minus g hat, theta. So now we've got something beautiful. We've got an integral and a delta function. And integrals and delta functions are built to cancel each other. So the integral over g can be done by just replacing g by g hat of sigma. So we get d zeta dx mu e to the power minus s of x g hat of zeta times delta fp of g hat. Now, we have been very careful to ensure that the action that we started out with was in fact wide invariant and diffeomorphism invariant. So this is an action as a function of g hat of zeta. But since the action does not depend on gauge transformations, I can cancel the zeta. And now we've got another beautiful thing. We've got an integral over gauge transformations over something that does not depend on that gauge parameter at all. It's just some constant that goes outside the path integral. In fact, the constant that goes outside the path integral was something we should have divided by anyway. We should have started by this. Volume of gauge transformation. Because you see, the path integral we were computing was infinite. or more precisely, proportional to the volume of diffeomorphisms. Because given any configuration, there's always a diffeomorphism you could use that. Okay? So the path integral we started out by computing, that we wanted to actually compute, wasn't really what I wrote down. It was that divided by the volume of these diffeomorphisms. Now, in lattice gauge theory, blah blah blah, we can make all this really precise. The volume of the diffeomorphism of gauge, compact gauge, this is a finite number. It doesn't matter. Here, nothing is finite. So we multiply. We pretend we started with this, and then we got this integral over this volume. We don't know what that volume means. We don't know what the integral means, but it's the same thing, so we cancel it. So we done this. And now we're sort of in business. You see, because now we've reduced our path integral to a path integral only over the x phase. G has been replaced by this G hat.
I might have asked you this before, but why does the instant constant matter? I mean, I know it matters in perturbation theory, whether you do it, but
why does it matter? No, it doesn't matter at all. And no constant matters for computing correlation functions. It's just that when something, to be sure whether something matters or not, it's nice to have a way of regulating it to get a finite number. Okay? So, you've got, it's just that vague unease.
okay.
Yeah. And once you can regulate it to get a finite number, you're sure it does not matter. Okay. Okay. So now this is great, but we've got this funny object, this delta FP of G hat. And we have to understand what this delta FP of G hat is. So, in order to understand what this delta FP of G hat is, any questions or comments about this? Okay? What? Yeah, there's been a lot of technical mumbo jumbo. But what have we done? What is this formula finally saying? You see, we were integrating over a lot of fields, but we had a lot of selection. Okay? So we can take that integral and break it up into an integral over gauge orbits times the volume of each gauge orbit. Think of the two-dimensional plane. Gauge orbits are the circle, so you have to integrate over which gauge orbit? That's R. Times the volume of each gauge orbit. That's 2 pi. Okay? Times this e to the power minus s, which depends not on where you are on the gauge orbit, but only on the gauge orbit, because it's gauge independent. That's what this thing has done. We've gone from integrating over all configurations to all gauge orbits. Because in any gauge orbit, there is one gauge transformation that takes you to G hat. And this delta FP of G hat is what? It is the volume of the gauge orbit. Why does the volume of the gauge orbit depend on G hat? Just like the volume of what you get from rotations depends on R in the two dimensions. The bigger circle or the smaller circle, depending on what you start. Okay? The conceptual point here is extremely simple. And the manipulations that we used, while a bit shady in infinite dimensions, in finite dimensional examples are just kosher, simple things. Okay, so you can think of this as an infinite dimensional generalization. Is this clear? Is this formula intuitive?
Can delta if you pull out the integral one, that it's not a function of
can the delta F be pulled out of the integral one? Yes, it can. Yes, it can. I mean, because it's not a function of x.
Yes.
But you see, we will need to get it straight because we will want to know whether, in the end, this whole thing depends on G hat or not. Okay, if we've done everything correctly, nothing depends on which fiducial metric we chose to gauge fixed on. That will be one of our final tests. Okay, and we will find that this whole part of the test, this part does, but the combination does. Okay, hang on for a little while before. At this point, you can just rest. Also, we're going to need to look at insertions. And some of the insertions we will need to look at will involve these things.
Really, the thing that you don't want to depend on the fiduciary metric are the measurable quantities like the correlation.
Correct.
So if it vanishes from that, then you're fine.
Yes, you're fine. You're fine. You're fine. Though we have to be a bit careful. You see, let me remind you of something. What are we really interested in this show? These are diagrams that you wrote in one of the lectures. But in computer's capturing amplitude, what you're really interested in is computing this following path integral. Okay? This path integral is the integral over all paths with some tubes that go out to infinity. We're going to use the state operator map to replace these tubes going out to infinity with insertions of corresponding operators. But the scattering amplitudes here will really map to the path integral with operator insertions, not necessarily, we'll see this precise, normalized by the path integral with no insertions. Sometimes we will see that the path integral with no insertions is 0. Hang on a minute. So what I'm saying is that the physically what are we supposed to do? It's supposed to be sum over all paths with certain boundary conditions. We replace those boundary conditions by insertions. So in string theory in this context, okay, what we're often going to be interested in is the actual path integral with particular insertions, not normalized by 1 over the partition function. Okay? So to get that straight, this will be very important. Okay, I request you to postpone these questions till, I believe it's not, yeah? To perhaps the end of this class. Then it will become clear. Okay, questions? Okay. So now in order to make this precise, useful thing, we need to understand what this delta FP of G hat is. Okay, so what was delta FP of G hat? Well, we have a definition of that. When d zeta, delta of G minus G hat of zeta is equal to 1 over delta FP. Now let's see, how do we actually compute this delta? You see, this delta function, this delta function we could firstly transform this to zeta inverse here by gauge levels. Okay? Now, as we change our gauge transformations, G varies over all values. But it only clicks when G is equal to G hat. So the entire contribution to delta FP comes from G expanded around G hat. So since G is equal to G hat times some zeta naught. Okay, this again by shifting the gauge parameter is the same thing as integral d zeta delta of G hat zeta minus G hat. Is this clear? Was this confusing anyone?
Yes.
Okay. See, we have this. Now we write G is equal to G hat times zeta naught. So this is equal to integral delta of G hat zeta naught zeta minus G hat. And then we change variables from zeta to zeta naught zeta. So I get this. Is this clear? So this Patikov determinant can be written in this form. And with this choice of variables, it only receives contributions from zeta in the neighborhood of identity. Alright. So now in the neighborhood of identity, an arbitrary gauge transformation is nothing plus an infinitesimal gauge transformation. Okay? So in order to evaluate this, we need to know how G hat transforms under infinitesimal gauge transformations. So how does a metric transform under infinitesimal? Well, metric goes to e to the power, let's say 2wg, wg, whatever. Let's put 2w. Okay, under infinitesimal Weyl transformation, delta g hat 2wg hat. Under infinitesimal Weyl. How does metric transform under infinitesimal diffeomorphism? Delta g here. Well, it transforms by the famous formula. Lie derivative of the vector field that generates this diffeomorphism. Okay. So plus del mu zeta mu plus del mu zeta mu. Okay. What does the measure?
The infinitesimal version of simplicity only means only the two omega scaling function.
What?
We have to do an additional diffeomorphism to get the addition. Getting of it. Is this the infinitesimal version of first line? This full thing?
No. This is the infinitesimal version of this,
No.
and this is the infinitesimal version of this is the infinitesimal version of this. Okay. Now, so this thing here becomes integral d omega d zeta mu. Really, you should argue that the gauge invariant measure diffeomorphisms about this point linearizes to a measure proportional to this. It's true. I mean, to the extent that. Okay. Times delta of what? Not this. 2 omega d hat mu nu plus del mu zeta mu plus del mu zeta mu. This thing is equal to 1 over delta x. What? Minus?
In the data function. Oh, sorry, that's the infinitesimal version. Okay.
Yes. Okay? So now we've got a manageable formula. We've got a manageable formula because now it's not abstract. But we will be even cleverer. Instead of trying to evaluate this thing, we'll be even cleverer. We will convert it into an integral. So we use the fact that delta of x is equal to e to the power I alpha dx, sorry, x integral d alpha by 2 pi. Okay? And we're extremely cavalier with all constant factors. Fix final overall normalization and consistency. Okay? So this becomes integral d omega d zeta e to the power I of, now let's call this beta mu times 2 omega d mu nu plus del mu zeta mu plus del mu. This was equal to 1 over delta x. We need an additional unit. Thank you. Why did beta mu nu have 2 indices? Because a metric had 2 indices. Yeah. Okay, great. Now let's look at this. Let's look at this for a while. Can any of these integrals be done easily? Yes, the W integral can be done easily. Because it just appears linearly. There were no derivatives. Okay? So it just gives you a constraint. What constraint does it give you? It gives you a constraint on beta. What's the constraint on beta? Beta is traceless. So we do the integral W, we get the beta mu. Everything is d e to the power I del mu zeta mu del mu zeta mu beta mu. Okay, so this guy here, and there's of course the zeta. This is just the integral over traceless symmetric tensor. Beta mu is a symmetric tensor because the metric was. Now we did the integral over traceless symmetric tensors. So we've got the zeta mu, the beta tilde mu, let's call it. E to the power I, beta tilde mu, mu zeta mu plus del mu, zeta mu. Okay, all very well. Now to make further progress, we'll make a particular choice of particular class of choices for G hat. We will choose G hat to be e to the power e to the power 2 omega times delta z. Okay, so what have we done? We've got a two-dimensional complex manifold. We've got some two-dimensional manifold. Okay, and we can always choose coordinates, at least locally, factorize. On this manifold, make one of our coordinates z, the other one z bar. Okay, we demand that the metric of this manifold is some particular, is up to a conformal factor, just what we had in flat space when we were doing our studies. Namely, the line element was dz. Okay, you can think of this as delta mu. This is what we're doing is choosing our fiducial metric to be delta mu nu up to a conformal factor. Okay. Now, once we've made this choice, let's try and understand now what the condition of tracelessness of beta is. The condition of tracelessness of beta is that beta z bar equals to 0, just like the condition of tracelessness of t. Is that dz z bar is equal to 0. So beta, instead of 3 components, has only 2, and these 2 components are beta z and beta z bar z bar. Is this clear? Is this clear?
Just one thing, it's important whether G hat is appendices or domain.
Appendices, domain. I mean, G mu nu is, let's call it that. Okay. This is in any x1, x2 coordinate system, and then z is x1 plus I x2. Okay, wonderful. So now we've got an integral over 2 zetas, zeta z and zeta z bar, and over 2 betas, beta z and beta z bar z bar. Okay. Now let us, in this coordinate system, more explicitly evaluate this action. So in this coordinate system, the action is more explicitly beta beta zz del z zeta z plus beta z bar del z bar zeta z. Question it up. Okay. Now this is the same thing as beta z bar. That's equal. I could have just done this. Del z bar. What the hell? Beta z bar del z of zeta z plus beta zz del z bar of zeta z bar up to perhaps factors of 2. Okay, so all I've done is take this guy and lower it, and I'll use this as also as up to potential factors of 2 and square root 2 that I'm not keeping track of. Its quadratic action means we normalize everything so that those factors, we can set the factor to whatever. This is our eventual action. Is this clear? Okay. Now, all covariant derivatives in this action, have to be taken with respect to this fiducial metric. Okay? What we want to do is to evaluate the dependence of this action on the fiducial metric, or on this omega, this Y transformation parameter in the fiducial metric. Where does the fiducial metric enter? It enters only in the Christoffel symbols. Okay? So let's try to evaluate this. Okay. So let's try to evaluate this. So let's see what we get. We get del z of zeta z bar is equal to del z of zeta z bar. Okay? Plus gamma z alpha z bar zeta alpha. That is the usual formulas of general relativity. Okay. But let's evaluate what this gamma z z bar alpha is. Okay. This guy here, gamma z bar z alpha, is proportional to del z of g. You lower this guy. So g z alpha plus del alpha of g z z minus del z of g z alpha. Are you with me here? All I've done is take this g. Note that g, that an upper index is a z bar upper index is proportional to a lower z index, and then use the usual formula for the Christoffel symbol. Is this clear? But now you note that here in our choice, gz was 0. We only have gz plus. So this is not that, and this is minus of this. So these two cancel. There's considerable confusion at the back. What is the?
Where did that integral come from?
Where did the integral come?
The one in the exponent.
Well,
The one in the exponent.
it was always there. Why was the integral always there? It was because we wanted a pointwise set. G is equal to something. Where is the integral? Let's see. Suppose you got delta f of x, which is a delta function that tells f of x minus f naught of x. Which is a delta function that tells you that pointwise the function f of x has to be equal to f naught of x. What is the exponentiation of that? That's e to the pi integral alpha of x times f of x minus f naught of x dx. Because at each point this has to be. That's what we were doing, right? G mu nu of x at each point had to be this value. So sorry, I may not have written it, but it was always there. Okay? Does that mean you've not understood anything since then? Okay? Is this clear? This point of the Christoffel symbols is clear? It's a general fact that if you've got a matrix with no z bar component, then the del z bar, del z of a z bar object is 0. I mean, the Christoffel symbol part is 0. Okay? So this guy vanishes, and it's clear that this guy, the Christoffel symbol there, will also vanish. And so we got this really. So this thing that when teaching one should never all over, it's just. But okay. So this thing becomes integral bz bar z bar dz of c of zeta z bar. Okay? Plus beta zz dz bar of zeta z. Notice here now we have only ordinary characters. There's no reference, ordinary characters. There's no reference to the fiducial metric. Now we want our full path integral to be independent of the fiducial metric. Independent of Weyl transformations. The action is independent of Weyl transformations. So this whole thing will be Weyl invariant, provided these objects, okay, these objects here transform under Weyl transformations trivially. Okay, so this is manifestly a Weyl invariant path integral, provided beta and zeta are Weyl invariant objects. What does that mean about how they transform under conformal transformations? They transform just like tensors. So, can you tell me how this guy will transform under conformal transformation? Like a primary operator of weight 2. How will this guy transform under conformal transformation? Like a primary operator of weight minus 1.
Z comes down.
Z comes down, that's true. But this guy transforms like, you see, it's important. Which objects are Weyl invariant? Zeta with an upper Z bar index. Okay? You see, if zeta mu is Weyl invariant, then G mu nu zeta mu is not Weyl invariant. Because G transforms under Weyl transformations. So it cannot be that both the vector with the upper index and the vector with the lower index are Weyl invariant. One or the other is true. Who is the Weyl invariant guy? This guy. Because it's for this, when written in terms of zeta with upper index and beta with lower index, that this covariant formula actually was independent of the Weyl factor. Okay? So zeta with an upper index is Weyl invariant guy. And that guy transforms with weight minus. Yes, that easily inverts. Okay, it's that a vector with an upper z bar index or tensor with n upper z bar indices transforms like a primary field with weight minus n, a holomorphic primary field with weight minus n. Something that transforms under diffeomorphisms and like a vector and while invariant. Okay, this is very important. It's very important because
it will take more than 40 minutes.
40 minutes unless.
We will take much.
Listen. Yeah. Okay. So it's very important that at every stage we could have either put the indices up or down, but it's with one choice of indices that the covariant derivatives become ordinary derivatives, and so the action is independent of the while factor. So with those choice of indices, that beta and zeta are while invariant derivatives. Every other choice of indices, they would also have to transform under while transformations so as to compensate for the while factors. In fact, we know how they would transform, just by raising and lowering the while invariant. But with this choice of indices, they actually while invariant. Okay? And therefore they transform under conformal transformations in a way that we've already understood. Okay? And with this notation, our action is extremely simple. It's beta z bar del z, sorry, beta r del z beta bar del z zeta. I'm just wondering whether with the in the BC system we have B del C, right? B del bar C. So I want this guy to be just sigma. Sorry, this is zeta. Okay, so the path integral e to the power is d beta, d zeta, including bars, it was equal to what? 1 by delta f. But now we've gone through this last exercise in the last 10 minutes or so. What was the purpose of the exercise? The purpose was to compute delta f. But we've got this nice path integral representation for 1 by delta f. Can anyone think of it? Okay, all of you don't. That's what is the way that to get a nice path integral representation for delta fp itself? Change the statistics of all fields. Everything here were real numbers. But integrals over Grassmannian fields have the property that the same path integral, that you just change where the determinant appears. If you get the determinant in the denominator for the integrals over commuting fields, the same integral gives you the same determinant in the numerator and denominator. So this equation is the same as the equation delta f is equal to db dc e to the power b bar del c bar plus b del bar c. B bar del C bar plus B del bar C. Next.
We had a line hanging around here.
Yeah, that's what we had. Yeah, probably won't. Let's put that out. Now, yeah, good question. What do we do? Where did I go? I did it more. Let's see. once we've converted this to a Grassmann integral, yeah, okay, it doesn't really matter. You see, once we've converted, all that this is getting the right integral. Now, if we put an extra factor of I or not, it will change the overall factor, determinant factor by a factor of I to some power infinity. We really only care about the dependence of this on the auxiliary metric G hat. Everything will be the overall number normalization of this. We'll fix by other requirements. We've been too crude to keep track of that. Okay, so that just goes into that. So whether we put it or not, it doesn't matter. I think the standard convention is to not put it. It's not a positivity or anything issue. This is integral Grassmann means. Okay, so we just will not put it. Okay, maybe I need to think a little more. I'll try to give by next class I have something better to say. I'll just drop the IIT. I don't think it matters very much, but maybe there's something more to say. Yeah. So this is I to the power infinity times delta I. We're going to worry those overall. Now, as I said, the overall factors for this integral we will work out by our means. We will need, by the way. Compute scattering amplitudes in string theory, as I said, it's the whole path integral. And we will need that, but we'll work out by our means. We'll work out by consistency. Okay. Excellent. But it's a good question. Yeah.
No, it's this seems like this whole way of getting the goal seems very gauge dependent.
Which gauge?
Through the
ZZ bar. Yeah, it's very dependent on the fact that we're choosing this. We're choosing the fiducial metric, this G hat, to have only a ZZ bar. Yes. Now, you see, that is basically the statement that we're choosing the fiducial metric to be something convenient. Okay? You know, what we're going to do is this. We're using the following mathematical fact. The mathematical fact is that all metrics, that the space of metrics in the two dimension can be broken up into the space of complex structures times y factors. Okay, so we're choosing a set of complex. Hang on a bit. Yeah, it's dependent. We'll understand this better.
Also, we talked about the invariance and the wire transformation. So, by fixing the dilution metric, we also fix the diffeomorphisms.
Oh yeah, but exactly. We fix diffeomorphisms as well as wire transformations, and in fact, all of the non-trivial part of the Vadipokov thing came from the diffeomorphisms. You see, the wild part was just a W, which we just did the integral. What that did is make beta or B traces. All this other stuff, this stuff is zeta, where it had its origin in the infinitesimal diffeomorphisms. Okay? But both were needed. Because it was the tracelessness that gave you the structure. Okay. So the Vadipokov determinant is precisely the path integral of the BC system. At what value of lambda? At lambda equals 2. Because B is a primary operator of dimension 2 and C is a primary operator of dimension -2. Is this clear? Okay? So this was the reason we studied the BC system in such detail in the previous class. That the BC system turns out to be the Vadipokov sector of the path integral of string theory. Oh, that was out. Okay?
Now your real action will have real fields with these Grassmann.
Yes. So the full path integral of string theory is what? The full path integral is integral dx dB dc e to the power minus s of x function of g hat minus sdc function of b and c and a function of g hat. Okay. now you see, we made lots of assumptions along the way, right? We could define this measure in a way that's wildly invariant. It's quite a startling assumption if you think about it. Because often to define a path integral, you need to regulate. Regulators are changed by changing scale factors, while transformations include scalings. So we made a lot of assumptions along the way. And now it's truth time. Right? Have we landed on our feet or not? We've got this nice formula, but is it making sense? What are the checks we get? There are many checks over this class to next. But the first one is a very simple one. It is this, that we did gauge fixing with a particular choice of G hat, but we were careful to allow some freedom in our G hat. This freedom with the e to the power 2 omega. Now the question we're asking is, does our path integral depend on this omega or not? If it depends on omega, something was wrong along the way, most likely wrong with the y dependence. If it does not depend on omega, we can go on to further checks. Okay? It's very similar in spirit to these zeta gauges of QED. Where you set some Lorentz invariant type gauges, okay, but with a number, and you keep them through to your calculations just to check that nothing depends on that number as a consistency check. Okay, so here nothing should depend on our fixing parameter. That's just a consistency check that everything that we've done is correct. If it does, we clearly have to try for. Okay, so now what I want to know. We will do this more carefully with insertions, which is what really interests us. But already at the level of partition functions. Okay? Already at the level of partition functions, I'm going to ask the following question. What can I say about the dependence of this partition function on the fiducial metric G? Okay? Now this is a simple question in conformity. Because we're no longer doing a path integral over matrix. Gi is just a fixed metric. And the action we apply is a simple action of conformity. The free boson conformity theory and the free BC system conformity theory. These are conformity theories we've spent many lectures on. We think we understand them to death. So, surely we should be able to understand how the action depends, how the path integral, how the partition function of this theory depends on the fiducial metric in which we study it, on which we study it. Okay. Now we've only kept track of dependence on this omega. Okay. Dependence on diffeomorphisms. Of course, we don't expect any dependence on diffeomorphisms. Okay. The non-trivial part of the dependence on the matrix is the dependence on omega. That's what we kept track of. So we can ask the following questions. What if we got a metric of the form that we do, which is G hat is equal to delta mu times e to the power w. Okay? How does the partition function depend on w? In order to address this question, let's change them. How does the partition function change as we change them? Okay? Well, clearly, it changes by del. Suppose we took set of G hat. It changes by del G mu times the change in the metric. Just delta W times G mu. Times G hat mu. Okay, so we change our G hat by changing, if we change our G hat by changing W from W to W plus delta W. The change in the metric is proportional to G hat and delta W. This is the change in the metric. And then, if we knew how the partition function changed under an arbitrary change of the metric, get this. But the derivative of the partition function with respect to the metric is an insertion of the stress tensor. And dotting the stress tensor with the metric, tracing it, is the trace of the stress tensor. Okay? So this is delta W times the expectation value of T. Okay, so it's delta W of X times T of X integrated. Okay, so we've got this lovely formula which tells us the delta Z. Really, if by expectation value we mean expectation value divided by function, let's say that that's what we mean, this will really be delta log Z.
What is the integral?
The integral is also this.
It's not T, right? The trace of T is 0.
What?
It's not T, T is T, Z, Z.
No, by T I meant trace of T. T. Okay. Okay. So this is equal to integral T mu mu of X delta W of X. Okay? And as Ronak said, you might at first think that great, the partition function does not depend on the Weil factor simply because the trace of T is 0. But are we sure that the trace of T is 0? The trace of T was certainly 0 on the plane when the metric was just delta Z. Are we totally sure that the trace of T is 0 for an arbitrary metric of this form? So let's check. In order to answer this, we're going to first, now we're going to do some abstract conformity theory again. We're going to first try to understand how the stress tensor. Okay, let me first see. I'm going to link two things again. I'm going to link what the value of the trace of the stress tensor is to the transformation properties under conformal transformation of T in the annual. Where does that link come from? So let me explain that schematically and then we go through the details. Suppose it was true, you see, naively T is equal to 0. Classically, certainly T is the trace of the stress tensor. T mu mu is equal to 0. And certainly it's 0 when our W function is constant. Certainly that's true. Okay, that's last few classes about that. Now, suppose it's not 0 when W is not 0. What that means is that
W is not constant.
That's not constant. Now, what that means is that it's 0 in a flat manifold, but non-zero away from flatness. Okay? So, whatever we get on the right hand side, just allowing for possibilities, has to be something that is correct. Yeah, diffeomorphism in measure vanishes when everything is flat and has the right dimensions. T is dimension 2. Well, there's basically one candidate. The only candidate is some number times the scalar function. Suppose insertions of T inside the partial template were actually equal to insertions of A times the scalar curvature. Okay, that doesn't contradict anything we know. And it's the most general possibility consistent with everything we know. You could ask, what about R square? But that's dimension 4, so we'll have to come to with a length scale. But there's no length scale. It will have to be like cutoff, divided by cutoff square, which goes to 0 as you take the cutoff. There is, but you have to build the length scale is in curvatures. It's got to be some local quantity built out of local invariants. So yes, we want the length scale, that's R. So you have to get something of dimension 2 just built out of local invariance. There's no, what I meant is that there's no parameter that you can solve out dimensions. Right? What about some other operator? Some dimension 2 operator that have to be there in the conformity. What about that? Well, if it was just T is equal to that operator, we would have seen it in flat space. That can't be. What about R times some other operator? There are no operators of dimension 0. Doesn't work.
But the action has the ghost part.
What?
The action has the ghost part.
Has the ghost part. Okay, good. So I need a better argument. Why can't we have operators of dimension 0? So Ronak saying, suppose you're in a non-unitary theory, like we are, why couldn't you have operators of dimension 0? Okay, it's a good question. Okay. So let me say, the real reason is that this term is going to be linked to the conformal transformation of T, as you will see. And if there was any operator other than just stuff built out of the metric, it won't work. Okay, so sorry, that argument was a bit facetious. If it was unitary theory, it actually would be correct. Okay, we need a better argument, as you say. Okay, let me take this as a provisional assumption that it can only be built out of curvatures, and you will see as we go along that this is anything else would be. Okay, now suppose this was the case. We'll see this by the end. Suppose this was the case. Okay, suppose it was the case, what can we say about it? What I want to do is to deduce something about the analytic part of the stress tensor from this statement. So I got a statement that T z bar is equal to okay. See, what do I want to say? What I want to say is that, look, suppose I've got del, let me make sure I'm not. I want to use now conservation of the stress. So, okay. Now, inside an insertion, inside such an partition function insertion, in which we've got no other operators inserted. Okay. If something like this were the case, then what we would have is that T mu nu would be equal to some prime, which is some factor of 2, times G mu nu times R. Because it would correctly tell us that the TZZ was equal to 0. TZZ was equal to 0. How do we know that? We know that just from rotational invariance. It's got spin 2. Just rotating in the Z direction. That must vanish. Okay. TZ bar Z bar must be equal to 0. So this rotational invariant guy was A prime times G mu nu times R. Right? If you take the trace of this, you come back to this. So these two are basically the same statement but coupled with some sort of rotation. Okay. Now suppose I have this statement. Now suppose I take B mu of T mu nu. Diffeomorphism invariance is assumed to be always preserved. Okay? Since B mu doesn't act on G mu nu, this is the same thing as A prime G mu nu times D mu of R. what is the statement? Now what is the statement? This statement is, so either we can keep this new index is free. This new index is free, so it could be either z or z bar, and that's just working out. So suppose that the new index was z. Suppose the new index was z, we would get del z bar of t z bar z plus del z t z z is equal to 0, is equal to whatever a g mu nu just a d nu bar. Okay, and similarly with the other index string, we get del z bar d z bar plus del z d z bar is equal to, and this was free index was z a del z bar. But del mu of d mu nu is always 0. It's conservation of the stress tensor. That should always be. Okay. And so we get that. No, sorry. Let me start. Two different manipulations. This is equal to 0. This is equal to 0. These are the equations I want. That's just conservation of the stress tensor. And then I use that this quantity del z of tzz, which is equal to del z minus del z bar of tz bar z minus x mu, and then is equal to minus del z bar by this equation, minus a prime del z bar g z bar z of r. Okay, so we get that del z tzz in conclusion is equal to minus del z of r with an a prime. So this is true for, so if this is true for insertions inside the path integral with nothing else, and if this equation is true, then it follows that for insertions inside the path integral with nothing else, this is true. Okay, so we've got, so what we got here is some sort of strange prediction. We've got a strange connection predicted between insertions of derivatives of tzz, okay, and the del z derivatives of r. So if this a prime was non-zero, it's making some prediction about insertions of derivatives of tzz and a prime derivatives of r. Now, sorry.
First equation you said del mu of t mu nu is something.
This one?
Right? Yeah.
Just ignore this. I'm never using this equation.
The true statement is that del mu t mu is 0, that's a conservation equation which is always true.
It's always true.
On any manifold. Then you write the first inequality which follows from the first equation.
So this equation
Yeah.
and this equation gives this.
If I just use this equation, then del mu t mu is not 0.
Well,
If I just add del mu on that, then del mu t mu is not 0.
yeah, if you just act del mu on that, then del mu t mu is not 0. So how can that be? That's a good question. Yeah, that's a good question. Give me. Give me.
So can't there be some harmonic term?
Surely I messed up somewhere. Sorry, I'll do that. Yes. Yeah, what are we doing? Give me.
Just to the index structure, there could be two possible terms in the second equation, right? Which is u mu nu r and r mu nu.
So that should be right.
So that is
Yeah, right. And that gets it. But why haven't I taken that? Just. And that would then allow for you're right. You could have I just messed up. So T mu could.
But then R Z has to be 0. Because dz is always 0, dz is 0.
Yeah, what's probably going on is that for metrics of this. So, what? Yes, it's clearly a terms of the.
Is gradient T mu always equal to 0 and vanishes only on shell?
Gradient TV on shell for what? And on shell for the conformity theory. Conformity theory is on shell. So that's fine. Shift vanishes sign insertion. That should always. Yes. R T mu nu. Oh yeah, clearly. Just. me start from the other end of it. Okay, I've clearly messed up here. Erase this from your minds, okay? You're right, Ornago, thank you. Sorry, this was clearly something badly wrong here. I'm going to erase this part of the blackboard. I'll start from the other end and see if we can fix it up. Sorry about this. Okay. We may have to do this next class, but let's see if we can just fix it up next time. That was a bad mess out, I'm sorry. Let's see if we can get the other end of this right. Okay, I'm just going to start by asking a simpler Bjorken formula theory question, which is how does T z z, this T, transform under y dimension? Okay, so under an arbitrary conformal diffeomorphism, under z goes to delta z is equal to epsilon z, z goes to z plus epsilon, we've seen, right, that delta t was equal to, so we had third derivative by 6, but there was 6 c by 12 epsilon triple prime of z plus 2 epsilon of z t plus epsilon l plus del also. This was epsilon prime and this was epsilon. We've seen this. Sorry, I'm trying to get the other part straight. Let me start from this end. I'm trying to make contact with this and let me start from here and make contact. Get that easy. Okay. 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 So under a coordinate change like delta z is equal to epsilon of z, okay, this is how the stress tensor changes. Now this part and this part are exactly the tensor transformation properties of T, as we've seen many times before. So the question we're going to ask is, what can we make of this part? Okay, now, see, suppose we have the metric. We have the metric which was ds squared, which is equal to dz bar. And we do the coordinate change. Okay, z goes to z plus epsilon. How does the metric change? Under this coordinate change, ds squared is equal to dz bar. But if z was equal to z prime plus epsilon of z prime, okay, if z was equal to z prime plus epsilon of z prime, we would get ds squared is equal to dz prime bar into 1 plus epsilon prime plus epsilon bar prime. Right, just by expanding it. Okay? So, the Weyl factor with which the metric transforms. Okay, so W, which is, so if we say that G mu, so we got G prime mu is equal to e to the power W G mu, where W is equal to del z epsilon plus del z bar epsilon bar. Okay, infinite. Everything is small. Okay. Okay, excellent. So, now what we want to do is the following. we've got that T transforms under this conformal transformation like this. This part we know as the tensor transformation. So this part here we want to interpret, okay, as some function of the Weil transformation. So what operation can we do on this? What operation can we do on this delta W? Okay, to produce this object. Well, it's clear between two analytic derivatives, because that epsilon bar is a function of z bar, so an analytic derivative will kill it. Okay, so the Weil transformation property of T, okay, is that delta T, okay, is that delta T at least under a small Weil transformation starting around flat space. Okay, delta T is equal to, or delta T. Now let's remember what this transformation was. Okay, what this transformation was. Now we worked this out very carefully last time. So this is to get the sign right. We worked with lowers. And was delta T what was our formula? Can somebody remember? Somebody remind me? Was it T is Z prime? Wasn't it this? That, yeah, T is, suppose we have Z prime. Okay, this was equal to del Z by del Z prime squared T of Z. So it was a formula for the new stress tensor with lower indices in terms of the old stress tensor. This was a final formula, right? Yeah, no, I mean, suppose we had, suppose it was tensor transformations. Yeah. So what we see is that delta T, which is equal to T prime minus T. Okay, is equal to C by 12 del Z squared of W, where in the case that G prime is equal to e to the power W and G is equal to was equal to 1. Okay? So what we see here is we've got a nice formula for the transformation. We've got a nice formula for the transformation of the stress tensor under an infinitesimal Weil transformation, at least about identity, at least about flat space. Okay? Now, of course, this formula for a transformation under the Weil transformation should be coordinate. Okay? What was the deal with having two Z derivatives here? The deal was because of this had to do Z derivatives. Okay? So, the transformation of T under an arbitrary Weil transformation in general must be the formula delta of T mu nu. Okay? Is equal to C by 12 del mu of W. Okay? But this formula immediately tells us that it is impossible for T Z bar. It is impossible for T Z bar in general to be 0. Because though we obtained this formula for the special case W is sum of analytic plus anti-analytic. Once we got the formula, it's just a formula for how something transforms under a Weil transformation. And it's true for any Weil transformation. Okay? So if I do a Weil transformation such that it's not the sum of analytic plus anti-analytic, so that del z bar of that Weil transformation is not 0. Okay? This object will just not be 0. Okay? So, now this is probably an easier derivation of what I was trying to get. So, okay. So, now, what I want, okay, I'll give you an easier, I'll correct what I got.
That's right. So two questions. First of all, should that be coherent derivative?
Well, everything is about to linear order around flat space.
Okay.
Okay?
So you're still there.
Well, we're still there, yeah.
Okay.
Yeah, right. If we can now probably promote this to some more sophisticated formula, varying, but at the moment I'm just for linearized fluctuations around flat space. Yeah. It probably will be true that the right formula is just this, but there may be some e to the power w, which we've not seen because we were doing it around flat space. So we should be, let's just be careful and keep it. There was another question.
No, sir, you thought about it.
Great. Okay. Now, what? Okay, so I'm going to backtrack on. I'll try to correct what I was trying to do yesterday, which was trying to imitate what Kulczynski did. So that I should just try to do what you want. Okay. So, but now I'll get to the formula I need. Okay. You see, this object here tells us how, in general, delta T mu transforms under a Weil transformation. But despite my mess up, that Arunabu and Yogesh had pointed out was wrong, the part that was certainly true was that T itself. Okay, we want some formula for what can this T be? T can't be 0 because otherwise this would be inconsistent. Okay? It cannot involve any other operator because if it involved any other operator, Weil transformation will have some contribution from that operator. Okay. So it has to be R or something like that times something. If there was that something involved an operator, then we get a term which is variation in R times that operator, which is absent. Okay, so the only operator that is allowed to be involved is identity. Okay? So this T here has to be some A times R by dimensional analysis. And the question is, what is A? Okay? But that's very easy to figure out. All we have to do is to figure out. Okay? So now we take this formula and make it a formula for the variation of the trace of this distance. Okay? If we were working to higher powers in omega, we would have to worry about whether we were varying the omega we use in taking the trace or not. Since this is already first order in omega, we keep the first order. We just trace with delta maybe. Okay? So there's no issue. So this formula here will give us that the delta of T mu is equal to C by 12 del square omega. Okay? But independently we know that the trace of the stress tensor here, okay, is A times scalar curvature. What we want to do is to fix what this A is in terms of sec. So all we need to know is how the scalar curvature changes after the Weil transform. Okay? Now, this requires some work or some looking up. Okay? Let's not do the work, and I've not yet done the looking up. So, if you look at Dirac things, for instance, they give you the transformation of the scalar curvature and general dimension under a Weil transformation. It always is that delta R is equal to some number which you have to check what it is it equals to. Okay? Times del squared omega. If you do it around flat space. Okay? I don't remember this number. I'll get it for you next time. Okay? It's 2, 4, half, something like that. Okay? So that number here is now identified with C by 12. Okay? So this logic allows us to determine what the number behind R is. Okay? So this logic allows us to determine what the number behind R is, and I'll quote this guy's result. And if I can find it. Yeah, he gets that T is equal to minus C by 12. That number was minus 1. Went that correctly. Okay. And he gets that T is equal to minus C by 12. Okay. I'll justify this. I'll give you the formula. We'll do carefully. The point I wanted to make, and sorry for that stupid mess up, the point I wanted to make is actually very simple. Where was all this coming from? You see, what we wanted was that our partition function was independent of the fiduciary metric. But the variation of the partition function with respect to the fiduciary metric was given by insertions of the trace of the stress tensor. And the trace of the stress tensor is minus C by 12 times R. Now for an arbitrary fiduciary metric, R is not 0. Like the simple formula for R in terms of second derivatives of finite e to the power omega. If you have G mu nu is e to the power omega times delta mu nu, some derivatives of delta mu nu will give you R. Basically, there's e to the power omega del square of that, something like that. But certainly not 0. So if we want that the partition function is independent of the fiduciary metric, that can only happen if C is 0. That's the only way we're going to have landed on our feet in our path integral derivation of the string theory. Now at first sight this might sound ridiculous, except that we know it's not, because we know that C is equal to minus 26 plus number of spacetime, no, number of x fields. Okay, that's all. That's number of spacetime dimensions. So C is 0 provided the number of spacetime dimensions is 26. Okay? So, if the number of spacetime dimensions was not 26, somewhere along the way in our manipulations, we messed up. Actually, it's easy to identify for you. This derivation more or less gives it to us. It's that the wild invariance of our action breaks down. The fact that things are depending on the fiduciary metric basically is telling you that the answer was not wild invariant. We assumed all through that physics was completely wild invariant. The measure of the action was wild invariant. And that's just not true outside the X26. As we sort of see from all of these results. For instance, the fact that the trace of the stress tensor is non-zero is telling you that you don't have wild invariance. Okay? So, if C is not equal to 26, we're out of luck. Doesn't work. Those formal manipulations will not correct. But when C is equal to 26, perhaps they. Okay? Now, we notice something else. We notice that C equals 26, that the number of spacetime dimensions is equal to 26, is what we obtained from another method in the second or third lecture of this course. Namely, by requiring Lorentz invariance of the spectrum, by quantizing the free string in a much cruder and simpler way. Now, what's the connection between these two statements? You see, both statements give us D equals 26 for consistency, but the consistency requirements seem very different. One consistency requirement was Lorentz invariance of the spectrum. The second consistency requirement was wild invariance. Actually, they're the same consistency requirement. Why is that? You see, because why did we expect to get a Lorentz invariant spectrum when we quantize string theory in the line code gauge? Line code gauge breaks Lorentz invariance. Why do we expect a Lorentz invariant spectrum? The reason we expected it was that physics cannot depend on gauge if gauge invariance is a true symmetric. So though our gauge breaks light cone invariance, physics should not, provided gauge invariance was a true symmetric. What gauge invariance we use to set light cone gauge? In particular, diffeomorphisms and Weyl transformations. So if Weyl transformations aren't the true symmetry of the problem, then how will that show up if you set a non-Lorentzian invariant gauge? It'll show up as a violation of Lorentz invariance, because then now there's no argument anymore that the physics should be Lorentz invariant. The argument was that if I made a gauge transformation, I could make a gauge transformation to a Lorentz non-invariant gauge, and therefore, since in that gauge Lorentz invariance is manifest, it must always be true because physics doesn't care about gauge. But if there's no gauge invariance of the theory, this is not true anymore. So lack of Weyl invariance inside the quantum physics of the theory, had it not been Weyl invariance, you would have expected it to show up in a non-Lorentz invariant gauge in all kinds of pathologies, in particular lack of Lorentz invariance. Okay? So these two symptoms of problems are actually the same. They come from the same source. The lack of gauge invariance explains both of them. Okay? So, we've got two different ways of saying that something goes wrong. You see, it's not 26. What goes wrong is basically that the path integral loses Weyl invariance outside the equals 26. Okay? So, now this path integral, the string theory path integral, there's a chance that it's making sense in 26 dimensions. Okay? But in order to make sure that it's making sense, we now want to compute something that we're actually interested in. Okay? What are we actually interested in? We're computing. We're interested actually S matrix elements. Okay? So what we have to do is to take this formula, this nice formula for this path integral, and turn it into a formula for S matrix elements. Once we have that formula, what we should do is subject it to every check you mentioned. Does this formula agree with all the consistency requirements that we know S matrix elements should have? Is it unitary? Okay. Does does it not produce ghosts? Various things that we will see. Okay. So what we should do is to take this path integral, this expression, this our understanding of how we've got these S matrices, and convert that into a concrete formula for S matrices. Understanding how we do path integrals, convert that into a concrete formula for S matrices, and then really study that formula. That passes every test. Then we've got a formula a proposed formula for scattering in quantum gravity, and you can, in some ways, forget about how you got it, as long as it makes sense. The heuristic part of the derivation. This is our formula. Okay? So that is our next job. Let me start it. 4-5 minutes. I'm sorry I wasted so much time on doing the wrong thing. I'll fix that also. But okay, let me just start this.
So where has quantum gravity come into the picture?
Where has quantum gravity come into the picture? Where has gravity at all come into the picture? Gravity came into the picture in the first couple of lectures. Because you remember when quantizing the string, we got spin 2 massless particles. Okay? And I mentioned then that we didn't belabor the fact that there is this folk theorem that the only interacting theory of spin 2 massless particles is a theory with diffeomorphism invariance. Any theory that has quantum mechanics and diffeomorphism invariance in it is a quantum theory of gravity. Okay? So, yeah. Okay. Just 2 minutes to set the stage for the next part. Okay. So, in order to compute the S matrix elements, we have to do our path integral more carefully than we did in the first one. Now, what did we not do carefully in the first round? The thing that we did not do carefully in the first round is the following. The thing we did not do carefully in the first round is the following. We did not carefully keep track of when you can achieve a particular gauge invariance. When a particular choice of a fiducial metric can always be achieved by a gauge transformation. Okay? And we also did not keep track of, if that can be achieved, whether that completely fixes gauge invariance. Now let's look at both those questions. Now that we understand these gauge transformations sort of well, let's look at both those questions in a little more detail. The answer to both those questions contained in this course Lagrangian. Okay, so we have this Lagrangian, which was beta mu mu, and then beta mu mu, and then del mu c mu zeta. Essentially this Lagrangian. Okay, now let's ask the following question. Suppose we have a gauge, so we've gone to fiducial network, and we've got a gauge transformation that is not fixed by the fact that we've gone to this fiducial network. What equation of, how do we characterize such gauge transformations? Just infinitesimal. Well, that would be a gauge transformation that leaves a fiducial metric unchanged. But how does a fiducial metric change under gauge transformation? By del mu zeta mu plus del mu zeta mu. So zero more of this operator about the fiducial metric, a zero more of this operator about the fiducial metric, okay, is a diffeomorphism that is unfixed. To have the Weil transformations at cup. This would be a diffeomorphism that was unfixed by a gauge condition. But as Ronald said, the full gauge symmetry was not just diffeomorphisms. It was this plus delta W and G. We have. Okay? So, now this delta W basically can always be used to remove the trace part. See, because any term here that is proportional to G mu can be cancelled by choosing the appropriate delta W. So what are we looking for? We're looking for some choice of diffeomorphisms plus a Weil transformation. Okay, some choice of diffeomorphisms plus a Weil transformation for which this combination is 0.
So every solution of del mu z mu plus del mu z mu equals 0 is also a solution of the bigger equation.
Well, but it's, you see, that's too restrictive. If you have del mu g mu plus, you only need but the traceless part, the part with trace removed of this thing equals 0. Okay, because the trace part is not 0, then you can always fix it by choosing that.
So what if you have some gauge transformation? You'll get general gauge transformations, right?
Yes.
You change Z however you want, to change W.
Yes.
Absolutely independently however you want.
Yes. So what I want is to solve that this is equal to 0. I'm looking for most general solution of this.
Yeah.
Now what I'm going to do is to fix delta W in terms of this. But just by taking place.
But then if there's a solution of this where this thing is not traceless, like
No, whether it's traceless or not. See, if this is equal to 0, then I can relate delta W to this.
Okay.
Just by taking trace of this equation.
Okay.
Okay? So d mu zeta mu is equal to plus 2 delta W is equal to 0. Okay? So delta W is fixed in terms of this also. Okay? So now what we want to do is to solve the equation d mu zeta mu plus g mu zeta mu, okay, minus half del dot zeta g mu is equal to 0. This equation is called the conformal killing vector equation. Okay, then you've got a killing vector up to the appropriately chosen scale factor to get rid of the trace part. All you need then is that the traceless part. Okay? And this, by the way, is exactly the operator that enters in the beta zeta or BC system. Because remember what we had? We had beta mu nu times d mu zeta mu plus d mu zeta mu. But beta mu nu was traceless. So it's only the trace part, the part of this operator with trace removed, that entered into the action. So in fact, you can explicitly, define a new operator after removing the trace. So you get exactly this. So we could write the full action as this. That's equivalent because theta was traceless. So this times this is 0. So this is how you should really think of the BC action, if you thought of it in the abstract notation. Okay? So you see that the solutions, the diffeomorphisms that are not fixed, are in one-to-one correspondence with the zero modes of the ghost C. Okay? So the C configurations that I am highlighted by the operator that multiplies C, this equation. Okay? And similarly, we have, so as we've seen, there is a one-to-one correspondence between zero modes of the C ghost and diffeomorphisms that are not fixed by a fiducial ghost gauge condition. Now, what about the other way around?
Sorry, repeat the last.
There is a one-to-one correspondence. You see, diffeomorphisms that are not fixed by the fiducial gauge condition are zetas that are annihilated by this operator. But this operator is precisely what appears in the C equation of motion. Okay? So, zero modes of the C field, things that, modes that obey this equation, do not enter the BC path integral. Because this part is just zero for that. Okay? So you take the path integral and expand in modes. Okay? And the zero modes of the C ghost are precisely the diffeomorphisms that are not fixed by our fiducial gauge condition. Moreover, what about the other way? What about the case when these gauge transformations weren't enough to get you to every metric? There are some metrics that cannot be obtained by performing gauge transformations on this fiducial metric. Okay? What is that situation? That situation is that we've got a fiducial metric, but there is a metric variation which is orthogonal to every variation that you obtain by acting with gauge transformations on the fiducial metric. Okay? Orthogonal under what inner product, it doesn't matter very much. We choose the inner product to be, the usual thing. If we've got a metric delta G mu nu, integrated over space, square root G. But that's precisely the inner product that appears here. This is the most general variation of the metric under diffeomorphism. Okay? Now, suppose you had something that was orthogonal to all such guys. Okay? Then if you plug that into the action here, because it's orthogonal to all such guys, the action will vanish. And therefore it is a zero mode of the B ghost. You see, suppose you've got a variation of G that is orthogonal to every variation that you can get from performing infinitesimal diffeomorphisms and wild transformations on the fiducial metric. Then such a transformation, by definition, you multiply this with an arbitrary variation, integrate, you get zero. Because it's orthogonal.
But this second one is, the conformal killing equation is always zero.
No. we're looking at general off-shell variation functions. We're doing a path integral. Okay, we've got path integral. We're not on shell. We've got path integral here, and for an arbitrary off-shell zeta, if you've got some metric variation that is orthogonal to the variation you get from an arbitrary Killing vector field, that is the kind of variation that cannot be obtained by performing an infinitesimal diffeomorphism. Is this clear? This is clear, right? See, what we are interested in is to see which variations of the metric are not obtainable by diffeomorphisms. Okay? If you have a notion of an inner product, as you do in our situation, there's an easy way to ask that. So, which variations of the metric are orthogonal to all variations that you can produce by an infinitesimal gauge transformation? So, this is the most general infinitesimal gauge transformation. Okay? And here we have anything that is orthogonal to all of these would, when plugged into this action, just vanish. So, coefficient of that variation would vanish. But if this action, how is that vanished? You can integrate by paths. So it is a zero mode of the B ghost. So what we see is something very nice is that the set of unfixed diffeomorphisms are in one-to-one correspondence with the zero modes inside the path integral of the C ghost. Okay? The set of additional parameters we need to add to our fiducial metric. Those variations of metric that cannot be achieved by gauge transformations, so you need to integrate over, not just that, you integrate over a class of fiducial metrics. And one-to-one parameters with the zero modes of the B ghost. Okay? So, keeping this in mind in the next class, we will more carefully redo our path integral derivation. Okay? To take into account the fact that not every diffeomorphism is fixed, diffeomorphism plus Weyl transformation is fixed, and not every metric can be obtained by diffeomorphisms from a. This will have to do with the zero modes of the C and B ghost, and we more carefully take that into account. And once we do that, we will end up producing a good formula for S matrices and strings. So that's fine.